Okay, so um, machine learning models are getting incredibly powerful, right? Pushing the boundaries of what AI can do.
Definitely. And to get that, that top tier performance,
Mhm.
we often end up with these giants.
Massive neural nets, yeah. Sometimes even whole ensembles working together.
And they're brilliant at extracting complex structure from huge data sets during training. Absolutely.
But here's the catch. Deploying these behemoths to where you actually need them, like on your phone or in a real-time system,
Or a device with limited power, yeah.
that's a major challenge. They're just too computationally expensive, too slow.
Cumbersome, really. So,
Mhm.
like, the big question becomes, how do you bottle up all that amazing performance, that insight from the giant?
And pour it into something small, fast, and efficient.
Exactly. And that's the core problem this deep dive tackles head on. We're exploring a fascinating technique called distillation.
Distillation, okay.
It's a surprisingly effective way to transfer the knowledge, and I use quotes because it's not just the parameters,
Right, it's more than that.
it's about the learned behavior, the generalization abilities. Transfer that from a large, powerful model or an ensemble into a much smaller, more manageable model.
One that's perfect for deployment.
Precisely.
And the insights we're diving into, they come heavily from a specific influential paper on this topic, co-authored by some big names.
That's right, including Jeffrey Hinton. And they start with this really great analogy that I think sets the stage perfectly.
The insect analogy.
The insect analogy, yeah. They observe that insects often have these distinct life stages, optimized for different tasks.
Like a caterpillar and a butterfly.
Exactly. A larval stage, like the caterpillar, is designed purely for consuming vast amounts of energy and growing, just eating.
Right.
Then the adult stage, the butterfly, is optimized for travel and reproduction. It needs to be light, mobile.
Different needs, different forms. Makes sense.
But in machine learning, we often try to use the same model, one form for both training, which is that energy-hungry part.
And deployment, the needing to be mobile part.
Yeah. And this analogy suggests maybe we shouldn't. Maybe we train a cumbersome teacher model to learn everything,
The caterpillar.
the caterpillar, right,
Right.
and then create a small, efficient student model,
Yeah.
butterfly optimized for the deployment task, and just transfer the teacher's knowledge.
Okay, that makes a lot of intuitive sense. Use a giant to do the heavy lifting of learning,
Hmm.
then pass that learned intelligence to a nimble model for the real world.
Mm-hmm.
So our mission for this deep dive is to really unpack this idea. What exactly is distillation? How does this transfer of knowledge actually happen?
And what were the results they found? Because some of them, like you said, are genuinely surprising.
Right. And what does this all mean for, building smarter, more efficient AI down the line?
Okay, so first maybe let's just quickly touch on why these large models and ensembles are so good at the training part.
Good idea.
Well, larger models, especially if you pair them with strong regularization techniques like, say, dropout,
Oh,
and particularly ensembles of diverse models, they're just excellent at capturing complex patterns in data and generalizing well to new, unseen examples.
and ensembles get that robustness by averaging predictions, right?
Mhm.
Smooths out error.
Exactly. But, as you pointed out, running these computationally intensive setups at test time, that leads to unacceptable latency and cost for a lot of applications.
Got it. So the old approach of just trying to shrink or optimize the big trained model doesn't quite cut it. The knowledge isn't just about size or parameter.
Precisely. It requires a bit of a shift in thinking about what knowledge in a trained model truly represents.
Okay.
It's not just the specific weights and biases. A more, powerful view is that knowledge is the learned mapping from inputs to outputs.
How the model responds across a whole range of inputs, not just the ones it trained on.
Yes. How does it respond? This perspective lets us think about transferring that learned behavior, that function, to a different, smaller structure.
And this is where soft targets come in. This seems like the real engine driving distillation.
It really is.
Because normally we train with hard targets. Like for an image of a cat, the target is 1 for cat and 0 for everything else. Very binary.
Correct. The hard target is crisp, unambiguous. It tells the model the right answer. But a large, well-trained model, one that generalizes well,
It doesn't just output a 1.
no. It outputs a probability distribution over all the possible classes.
Yeah.
And those probabilities for the incorrect classes, even if they're tiny, they aren't just noise.
They contain information.
Valuable information
Yeah.
about how the model generalizes.
Ah, like that example in the paper. Show a model of BMW. It predicts BMW, high probability, sure, but maybe tiny probability for garbage truck.
And even tinier for carrot.
Right. That nuance, that slight leaning towards something conceptually similar but wrong, that tells you something about the features the model learned.
Precisely. These relative probabilities for the wrong answers generated by the large teacher model, those are the soft targets.
Okay.
They encode the teacher's understanding of the similarity structure of the data, how different inputs relate to each other. And the small student model is going to be trained to mimic this rich, nuanced distribution.
Not just the single right answer, it learns the teacher's thought process in a way.
That's a good way to put it.
Okay, so how do you actually do that? Train using these soft targets.
Well, you train the smaller model on a transfer set. Often this is just the original training data.
Okay.
The key difference is, instead of focusing only on the hard labels, you use the soft probability distributions produced by the big teacher model as the targets for the small student model.
So the student's goal is to match the teacher's probability outputs.
Exactly. Its training objective is to match those soft targets.
And this is where temperature comes in, which I thought was pretty clever. The standard softmax function turns the raw scores, the logits, into probabilities.
Yes, the standard softmax uses a temperature parameter, T. Usually it's just set to 1. The formula involves exponentiating the logits divided by T. So when T is 1, you get your normal probabilities. But if you crank up T,
Increase the temperature.
you soften the probability distribution. It makes the probabilities for all classes more uniform, spreads the probability mass out more.
Okay, less peaky.
Right. And crucially, this also makes the differences between those smaller probabilities for the incorrect answers much more pronounced, easier to distinguish.
Ah, okay. So the cumbersome teacher model generates its soft targets using a high temperature.
Correct.
And then the small student model is trained to match these soft targets, also using that same high temperature.
That's the procedure. Training with a high temperature forces the small model to really pay attention to the relative magnitudes of those small probabilities for the wrong classes.
Because that's where the teacher's nuanced understanding is most visible.
That's where that valuable information about data similarity and generalization behavior lives. And then, once the student model is trained,
You turn the temperature back down.
yep, revert its temperature back to T1 for normal inference. And that gives you the sharp, decisive predictions you need in practice.
It's like showing the student a blurry picture from the expert's view where the subtle similarities pop out instead of just a sharp photo of the right answer.
That's a good analogy. And the paper also notes if you do have the original correct hard labels for your training data, it's usually beneficial to incorporate them too.
Oh.
You can train the small model using a weighted average of 2 objectives. One trying to match the soft targets from the teacher at high T,
Uh-huh.
and another trying to match the hard targets at T1.
And they found it often worked best to give a much lower weight to the hard target part.
Yes, which really highlights how much valuable signal is packed into those soft targets, sometimes even more than the hard labels in this context.
Interesting.
They also point out an important detail. When you combine objectives like this, you should scale the gradients coming from the soft target objective by T squared.
T squared, why?
It helps maintain the relative influence of the soft targets consistently as you adjust the temperature during experiments or tuning. Just a technical detail for getting it right.
Got it. And this idea of mashing the logits directly, the pre-softmax scores, that had been explored before, right?
Yeah.
How does it relate?
Yeah, the paper shows that training a student to match the teacher's logits is actually equivalent to distillation, but only in the limiting case where the temperature goes to infinity.
Ah, okay, a special case.
Right, assuming the logits are zero mean for each input. But they suggest, and actually show evidence for it, that using lower finite temperatures in the general distillation approach can be better.
Why is that?
Well, finite temperatures implicitly kind of ignore or downweight logits that are extremely negative compared to the others.
Okay.
These very negative logits might be less constrained during the teacher's training, potentially a bit noisy. So ignoring them to some extent can be beneficial, especially if the student model is very small or has limited capacity.
Right, you don't want it focusing on potentially noisy signals. Okay,
Yeah.
that gives a much clearer picture of the mechanics. But the real test is always the results, isn't it?
Always.
They ran some quite surprising experiments, starting with the classic MNS dataset, handwritten digits.
Right. They trained a relatively large neural net on NNest, used significant regularization, and got a respectable result. 67 test errors.
Pretty good.
They also trained a smaller neural net, same architecture, but with no regularization at all. Unsurprisingly, it did worse, made 146 errors.
Okay, so a clear performance gap there between the big regularized model and the small unregularized one.
A clear gap. Now, here's the really interesting part. They took that same smaller net
Uh-huh.
and trained it only by having it match the soft targets generated by the large teacher net
Yeah.
using a high temperature of 20.
So just learning from the teacher's probabilities.
Exactly. This smaller distilled net with no other regularization achieved only 74 test errors.
Wow, 74. That's almost identical to the large teacher model's 67 errors.
Pretty much. By just learning from the probabilistic outputs of the bigger model, the smaller net closed almost the entire performance gap.
It got nearly the same results as the large, complex, regularized teacher without needing all that complexity or the explicit regularization techniques itself.
That's a massive transfer of generalization ability right there.
Incredible.
And they saw similar effects even when they used a radically small model, one with only 30 units per hidden layer. Super tiny.
Yen for that one.
For that extremely constrained model, they found that intermediate temperatures, like between 2.5 and 4, worked best.
Supporting that idea that ignoring the most negative logits can help when the student model is really capacity limited.
Exact.
And then there's that fantastic story about the mythical digit 3 experiment that really drives home what kind of knowledge is being transferred.
Oh, that experiment is brilliant. Just a fantastic demonstration. They trained a small distilled model on MDZIF, but get this. They deliberately removed every single example of the digit 3 from the training data.
Wait, completely. The model never saw a 3 during training.
Never saw a single image of a 3.
So you'd expect it to have absolutely no clue what a 3 looks like or how to classify it.
Logically, yes. But remember, it was trained to match the soft targets of a large teacher model that had seen plenty of 3s.
Okay. So what happened when they tested it?
Well, initially it made a lot of errors on 3s because the output bias for the 3 class was essentially 0. It had no reason to predict 3.
Makes sense.
But then they simply adjusted only the bias for the 3 class based on performance on a separate validation set or the test set itself.
Just nudging that one bias term.
And the distilled model correctly classified 98.6% of the test set 3s.
That is incredible. It learned about the concept of 3 without ever seeing one. How?
By learning how the teacher model saw the relationship between other digits and the missing 3, like maybe an 8 is kind of similar to a 3 in the teacher's probabilities, or a 7 is very different.
It learned the similarity structure from the soft targets of the other classes.
Precisely. It shows that the knowledge about how a 3 looks its features, its similarity to other concepts, was implicitly transferred through the soft targets provided for all the other digits.
The teacher's nuanced probability distribution was enough to teach the student about classes it had never directly observed.
Amazing. It really highlights the richness of the information in those soft targets.
Okay, so moving beyond MNEST, they also tested this on a much larger, more real-world problem, speech recognition.
Yes. They used a sophisticated DNN acoustic model, the kind of thing used in production systems like Android voice search back then.
Right.
They trained an ensemble of 10 such models, and then they trained a single distilled model of the same size and architecture as one of the baseline models.
And this was on a huge data set.
Massive, around 2,000 hours of speech, which translated to about 700 million training examples. It's a serious test case.
Definitely demonstrates practical applicability at scale. What were the results?
Okay, so the baseline single model got 58.9% frame accuracy and a 10.9% word error rate, or WER. Lower WER is better in speech recognition.
58.9 and 10.9. Got it.
The ensemble of 10 models, as you'd expect, did better. It reached 61.1% frame accuracy and a lower WER of 10.7%.
Okay, so a noticeable improvement from the ensemble. But of course, at 10 times the computational cost for inference.
Exactly. That's the trade-off. Now, the single distilled model,
One trained to mimic the ensemble.
it achieved 60.8% frame accuracy and that same 10.7% error.
Wait, hold on. The single distilled model got 60.8% accuracy. That's nearly all the gain the ensemble got over the baseline.
Over 80% of the frame accuracy improvement, yeah.
And it got the full 10.7% error, the same as the 10 model ensemble.
That's the key takeaway. It transferred nearly all the accuracy improvement and the entire word gain from the massive ensemble into a single model.
A single model that's no more expensive to run than the original baseline.
Exactly. This is enormous for practical deployment. You get ensemble-level performance without the prohibitive cost and latency. Huge win.
That's incredibly powerful. But okay, what about data sets that are just so big, like that JFT data set they mentioned?
Yeah, JFT. 100 million labeled images, 15,000 different labels.
On that scale, training even one massive model takes months, right? Training a full ensemble seems
Yep.
impossible.
Computationally impossible, pretty
Eh.
much, or at least wildly impractical. And that's where they introduced this complementary idea, ensembles of specialists.
Specialists. Okay.
When you have a data set of that scale and complexity, especially with lots of fine-grained classes that are easily confused,
Mm-hmm.
think different types of bridges, specific car models, bird species.
Things that look really similar.
Exactly. Training a single general model to handle everything perfectly is hard.
Hmm.
And training or running an ensemble generalist models is, as you said, infeasible.
So instead of many generalists, you train one generalist and lots of experts
Yeah.
focused on specific tough areas.
Precisely. The ensemble consists of one generalist model, trained on all the data and all the classes, and then many specialist models.
And each specialist focuses just on distinguishing between classes within a small specific subset where confusion is common.
Exactly. Like a specialist just for distinguishing different kinds of dogs or different models of cars from the 90s or whatever.
Makes sense. Their job is narrower.
Much narrower. Their softmax output layer is much smaller too. It only covers their specific expert classes, plus one extra dustbin class that represents everything else.
The none of the above option for them.
Kind of, yeah. And a crucial implementation detail. These specialist models are initialized with the weights of the generalist model,
Oh, okay. So they get a head start.
the strong starting point.
Mm-hmm.
They inherit the generalist ability to process lower-level visual features, presumably.
And then they're trained on data that's heavily weighted towards their specific area of expertise.
Yes, they oversample the data from their special subset during training. They also see some general data to stay grounded, but the focus is on the hard distinctions within their group. And they need a bias correction for that dustbin class because of the oversampling.
How do they figure out which classes should go into these specialist subsets to begin with? With 15,000 classes, that seems tricky.
They used a pretty clever method. They looked at the covariance matrix of the generalist model's predictions on the training data.
Okay. What does it tell you?
If the generalist model frequently predicts high probabilities for two different classes at the same time for the same input image.
It means the model is confused between those two classes.
Exactly. It suggests those classes are confusable for the generalist, and therefore they probably form a good candidate subset for a specialist to focus on.
And that method doesn't require you to know the true labels or have some prior knowledge of which classes should be confusing.
Nope. The model's own behavior tells you where the confusion lies. The paper gives examples like separating predictions for tea party and various showers like bridal or baby showers, or differentiating between types of bridges or car models, things the generalists struggled with.
Okay, so you've got this mix. One generalist, many specialists. How do you actually combine them to make a final prediction at inference time?
It's typically a two-step process. First, the generalist model runs and quickly identifies the top, say, N, most likely classes for the input.
The broad strokes.
Right. Then you only activate the specialists whose specific subsets overlap with those top N classes predicted by the generalists. You don't need to run all the specialists.
That saves computation.
Definitely. Then the predictions from those relevant specialists for the classes they cover are combined with the generalists' predictions for those same classes. They mention using KL divergence minimization to blend the distributions effectively.
Okay. And did the specialist approach actually work? Did it improve results on that massive JFT dataset?
Yes, significantly. They started from a baseline single generalist model that had 25.0% top one accuracy.
25%.
By adding just 61 specialists covering some of these confusing subsets, they boosted the overall accuracy to 26.1%.
Okay, 26.1%. That's a 1.1% absolute jump, which is a 4.4% relative improvement. Pretty decent on such a hard task.
It is. And critically, these specialists train much, much faster. We're talking days, instead of the many weeks or months it takes to train a full generalist from scratch.
And you can train them in parallel.
Highly parallelizable. Training different specialists doesn't depend on each other.
So you can potentially scale up the system's performance just by identifying more confusing subsets and training more specialists independently.
Exactly. And the results supported this. They showed that the accuracy improvement tended to be larger for classes that were covered by more specialists. It's a very encouraging sign for scalability.
Now, how does distillation, our main topic, fit back into this specialist approach?
Oh, that's a really interesting connection they make, showing the versatility of distillation. Think about it. Specialists are trained on highly enriched data from their narrow subset,
Right, they see way more examples of their specific classes.
which makes them prone to overfitting to those specific classes, potentially forgetting some of the broader context learned by the generalist.
Okay, yeah, that makes sense.
So the paper suggests, and the speech experiments we talked about strongly support this, that you can use the soft targets from the generalist model
The teacher.
as targets for the non-specialist classes during the specialist training.
So the specialist learns its specific distinctions using hard labels, but learns about everything else by mimicking the generalist probabilities.
Essentially, yes. It acts as a powerful regularizer. It helps prevent the specialist from overfitting its narrow domain and helps it retain the broader knowledge learned by the generalist about how its classes relate to the outside world.
Even if the specialist model itself is smaller than the generalist.
Exactly. So you're using distillation not just for the final student model, but as part of the training process for these intermediate specialist components. It's both knowledge transfer and a unique form of regularization.
That connection is fascinating. Let's dig a bit deeper into that specific idea, soft targets as regularizers, because those speech experiment results you mentioned earlier sound quite striking.
They really are. A very clean demonstration. They took the baseline speech model architecture, a pretty big model, 85 million parameters, and they wanted to test the regularizing power of soft targets directly. So they trained this model on a tiny fraction of the total data, only 3%.
3% of 700 million examples is still 20 million examples. Not tiny, but tiny compared to the full set.
Exactly.
Yes.
20 million examples. When they trained this big model using standard hard targets on just that 3% of data,
What happened?
severe overfitting. The accuracy on the training data shot up to 67.3%, but the accuracy on the unseen test data plummeted to a poor 44.5%.
Ouch.
They actually had to stop training really early because the test performance was just collapsing.
Yeah.
Classic overfitting. You just memorize that small training set.
Right.
But then they trained the exact same model architecture on the exact same 3% of the data. But this time, instead of hard targets, they used the soft targets generated by the teacher model.
The teacher that had been trained on the full 100% data set?
Correct.
And the difference was?
Huge. The test accuracy jumped dramatically to 57.0%.
From 44.5% to 57.0%, just by changing the targets.
Just by changing the targets. And it didn't overfit significantly at all. The training accuracy was 65.4%, very close to the test accuracy. It converged smoothly, no need for early stopping.
Wow. And how did that 57.0% compare to the original baseline trained on all the data?
That's the kicker. It recovered almost all the performance. Remember, the model trained on the full 100% data set using hard targets got 58.9% test accuracy.
So 57.0% versus 58.9%, training on only 3% of the data, but using soft targets from a fully trained teacher got you almost the same generalization performance as training on the full data set yourself with hard targets.
Exactly. The soft targets are acting like this super concentrated form of the knowledge and the regularities contained in that massive original data set.
It really demonstrates how much rich information about the underlying structure, beyond just the correct label, is captured and transferred through those soft probabilities.
It makes soft targets a remarkably effective way to regularize a student model, especially if your own training data is maybe limited or noisy or just a small fraction of what the teacher saw.
Okay, let's try and bring all of this together then. What are the big takeaways? Why does this whole concept of distillation and maybe these ensembles of specialists using these ideas, why does it matter for someone building or using AI?
Well, I think the fundamental impact is enabling the deployment of really powerful, high-performing AI models that would otherwise just be too large, too slow, or too expensive to run in many real-world applications.
Right, bridging the gap between training capability and deployment reality.
Exactly. Distillation allows you to train that powerful teacher model or that complex ensemble using all the compute you need, and then efficiently transfer that learned capability, that knowledge, into a smaller, faster model.
A model that's suitable for deployment on, say, edge devices, mobile phones, real-time systems like voice assistants.
Or anywhere where computational resources are constrained. It makes that high-end performance accessible.
And the specialist concept, that provides a path to scale up training for these truly massive data sets, like JFT, with thousands of confusable classes.
Yeah, it offers this modular approach.
Right.
Create these experts that can be trained in parallel, focusing on the hard parts.
And potentially using distillation again, as you said, to help manage their training, prevent overfitting, and maybe even consolidate their combined knowledge later on.
Right. Ultimately, it's about decoupling the requirements of training from the requirements of deployment. Use the heavy machinery for learning, then use distillation to package that learning efficiently for practical use.
It just makes advanced AI much more practical and efficient.
That's the goal.
The paper even sort of muses on future directions, right? Like maybe distilling the knowledge from that whole ensemble of specialists back into a single, maybe even larger generalist net.
Yeah, they hint at that. Could you create an even better single model by consolidating all that specialist knowledge? It suggests the ways we can transfer and consolidate knowledge. Well, there's plenty of room left to explore there.
Definitely feels like an active area.
This whole idea of distillation, especially thinking back to that MNIS-3 experiment, it really makes you stop and think, doesn't it?
It does.
If a model trained on vast data transfers so much valuable knowledge, not just about the right answers, but about the subtle relationships, the near misses between concepts through those soft targets, the wrong answers. What does that tell us about how we generalize?
Yeah, is human understanding also deeply tied to recognizing these nuanced similarities and differences, not just knowing the hard facts?
It feels like it might be. It suggests generalization involves more than just memorizing labels. It's about building this rich, interconnected map of the world or the data space.
It's a good way to put it.
And maybe, just maybe, if we're trying to teach complex subjects to other people, perhaps focusing only on presenting the hard facts, the right answers, isn't always the most effective approach.
Interesting thought.
Maybe we should pay more attention to illustrating how concepts relate, what they're similar to but still distinct from, explaining that landscape of potential misunderstandings or near misses. Kind of like how the soft targets guide the student model.
Exactly. It's just a fascinating idea for how we might think about learning and teaching itself, inspired by how these models transfer knowledge. Lots to chew on there.